welcome our last speaker, Nam from Euronova, and he will talk about sterile synchronous parallel iterations on Flink.
All right, thank you for the introduction. So here are the very brave who stay till the end. All right, so I work for Euronova in the research and development department. So first of all, who are we? Euronova, our motto is that we see ourselves as a team of passionate IT experts who are devoted to providing knowledge and skills to people with great ideas. And in practice, that translates to this fact. We have consultants on one hand, working at customers, who provide our R&D department with challenges. On the other way, we in the R&D department, we provide these customers with cutting-edge solutions in fields such as data science, distributed computing, software engineering, and big data. We are very active in research. Since 2009, we have led many PhD theses and master theses in collaborations with universities, and we are greatly involved in open source development also. And so, in that context, we have chosen Flink to be like our playground for research and for implementing our ideas concerning big data and distributed processing. And so, Flink is an amazing piece of software. It does a lot of things. It does batch processing. We have seen a lot of things about stream processing. And one thing it does also is iterative algorithms. So iterative algorithms are tasks in which you have a unit of work called the iteration that is repeated a certain number of times until you've reached a certain criteria of convergence where you can stop iterating. And so let's illustrate that with an example, like the task of digging a hole. That is an iterative task, meaning that you get your shovel, you remove some mud, and you repeat that again until your hole has the dimensions that you require. Now, I'm fully aware that Flink does a lot of things, and at the current time, it does not allow you to dig holes for real. Maybe one day it will come, but not now. But let's just take that as an example. So digging a hole is an iterative task. And you say, I have one worker, I give him one shovel, and he digs my hole. What happens, because we are in Flink, we can do that in a distributed way. So I will take 10 other workers, and I give them each one shovel. And so what will happen? I will expect my hole to be dug 10 times faster. In reality, that's the kind of thing that can happen. You give your 10 workers each one shovel, and they end up waiting for only one worker. And they just wait for the worker that is kind of straggling the whole process. That's awful. Why does that happen? The fact is, for doing iterative tasks in parallel, nowadays, one of the most popular paradigms is the bulk synchronous parallel iterations. And in that paradigm, you have workers synchronizing their results after each iteration, meaning that they work on their part of the solution, they dig a part of the hole, and then they wait for each other, they synchronize their results before going on. And in that scenario, there will always be one worker that will be struggling behind. There will always be a kind of struggler in this situation. And so you will always end up with having workers waiting for each other. And that causes more impact yet if in very large clusters. So the fact that all your workers have to wait only on one, you'll get massive hit on your performance the bigger your cluster is. And that's not what you want. What you want in reality is this. So you give each worker a shovel, and you expect them each to work on their part of the solution without waiting for each other. And so how do you realize that? So one way of tackling this problem is by using a paradigm for parallel iterations called the sterile synchronous parallelism. And that is what I'm going to talk about in this presentation here. And these are the results of a research project that we have conducted using Flink as our playground. And so on the first part, I'm going to talk to you about the sterile synchronous parallel paradigm and how we managed to implement that within Flink. so that we can tackle the straggler problem within the core runtime of Flink. And in the second part, I'm going to talk to you about the distributed Frank-Wolf algorithm, which is a optimization algorithm that we have implemented using stealth synchronous parallelism. And I'll show the results that we had and some of the nice properties that it involves. So let's head first to the part where we talk about stealth synchronous parallelism. And so I've briefly mentioned the straggler problem. What is it exactly? In a distributed processing framework, there are many sources of stragglers, meaning there are many causes that can lead to the fact that you have one worker that is slower than the others. And that can come from hardware heterogeneity, meaning that all CPUs are not equal. You can have a skewed data distribution in the way your problem is scheduled and partitioned. Or you can have garbage collection in the case of very high-level languages, which Flink is, and which most of the frameworks are nowadays. And these are sources of straggling that are not predictable and cannot be solved from the point of view of the scheduling. Meaning that if you have a straggler at one iteration, you cannot just try to reschedule the task from that straggler on another worker at the next iteration. Because before you know it, at the next iteration, there will be another worker that will be the straggler. So that's something that you cannot solve from a pure scheduling point of view, because it's independent from the framework. And that is particularly true in the case of data center operating systems, such as Mesos, in which you have your cluster, and every one of your workers is competing. So all the clusters are competing over the resources in the cluster. So you have workers that will execute tasks from other frameworks as well, and not only your own framework. So in that context, let me just go first into the basics of how both synchronous parallelism work. So in both synchronous parallelism, there is that explicit synchronization barrier, meaning that workers do the work they have to do during one iteration, and then at the end of each iteration, they just synchronize with each other, they shuffle their partial results, so that at the next iteration, they can begin to work with an updated state of the solution. And so on. After each iteration, they share their findings, they synchronize them before moving on to the next iteration. In stealth synchronous parallelism, the thing that is proposed is that we remove that explicit synchronization barrier, meaning that after each iteration, each worker can continue working directly, immediately on the next iteration without synchronizing its partial results with the other workers. We define what we call the staleness bound, because obviously we cannot leave any worker working indefinitely without synchronizing with the other workers. So we put a bound on the staleness, meaning that we fix the maximum amount of iterations that the fastest worker can be ahead of the slowest one. So in that example here, you have a staleness bound of 1, meaning that the fastest worker can be ahead of the slowest one of maximum 1 iteration. And if we look at things that way, both synchronous parallelism is just a case where your staleness bound is equal to 0. So now that we remove that explicit synchronization barrier, how do we still keep workers up to date? In stealth synchronous parallelism, we are going to use a component called the parameter server. And that's an external component that the worker can reach out to. And in that parameter server should allow the workers to write the intermediate results, aggregate the intermediate results from all the workers, and allow workers to read the latest state of the solution from the parameter server. And so in practice, how does that work? we have a worker finishing one iteration, and he just logs its partial result in the parameter server here. Same goes for this worker. And that means that the fourth worker here, when he finishes its fourth iteration, is going to read from the parameter server the latest results that have been written already by worker 1 and 3. And so he goes on its fifth iteration on the basis of the partial results already aggregated from worker 1 and 3. And this is the mechanism that we have implemented within Flink in the context of this project. So what does Flink need in order to enable still synchronous parallelism? First thing that it needs is a new iteration control model that allows for this behavior. And the second thing, obviously, is the parameter server. So how have we modeled the iteration control model for Flink? So what we need is we have workers performing the iterations, and what we need is a kind of component that keeps track of the state of the slowest worker in the cluster, so that all the workers can refer to that state, just to know if they are within the staleness bound, and just to know if they can go on with their iterations. And so in practice, how does that work? From the point of view of the worker, all it does is checking if his number of iteration, so that's what we call the clock here. So the clock is the number of iteration at which the worker is. The worker checks if his clock is within the staleness bound. And the cluster-wide clock here refers to the clock, the smallest clock in the cluster. That is the clock at which the slowest worker is currently in the cluster. So given these values, the worker checks if he's still in the staleness bound by checking by using the cluster-wide clock. And then if he is still in this bound in which he is allowed to continue without synchronizing, he does his iteration work. Then he increments his own clock value, and he sends that to the clock synchronization sync, whose work is to keep track of all the clocks in the cluster. Otherwise, the worker is going to wait until he is again within the bounds of which he can continue to iterate. And so, from the side of the clock synchronization sync, what this component does is gathering all the clock from the workers in the cluster, and at each time it receives a new clock value, it determines the new cluster-wide clock value, and that is the minimum value of clock among all the workers in the cluster. And if that value has changed, the clock synchronization sync then broadcasts the cluster-wide clock to all the workers in the cluster. So how do we implement that in Flink? So currently, how do the iterations work in? How are the iterations managed within Flink? So we have that when you schedule an iterative task, it is scheduled in parallel, and each of the parallel paths here represent a parallel iteration. All these parallel iterations are connected to a component that is the iteration synchronization task. And that iteration synchronization task represents the synchronization barrier. So each time you have an iteration finishing here, there is a worker done signal that is sent to the iteration synchronization task. And he sends the worker done signal and then waits for the synchronization barrier to complete. On the side of the synchronization task, once it has received all the worker done signals from all the parallel iterations, it broadcasts back a all worker done message, that will signal to the iterations that they can move on the next iteration. So in our case, what do we need to modify in order to implement the still synchronous parallelism? So the first thing we have to remove is that synchronization barrier and replace that with a mechanism that keeps track of clocks and broadcast a cluster-wide clock. Second thing we need to do from the side of the workers is prevent them from waiting for a signal before going on the next iteration. And so we implement a behavior on which they finish the iteration, send their clock, and have to determine whether they can continue or not, to determine if they are in the staleness bound, given the cluster-wide clock and their own internal clock. So just for the sake of completeness, in each iteration path here, Flink breaks down the iteration into 3 stages. That is the head, the intermediate, and the tail. And the data flows through the 3 stages. And at the end, a back channel is implemented to forward the results at the end of the iteration to the head. And that is what we have reused. We have reused directly. The way we have implemented SSP leads to components that are directly Dropin Replacement into the current iteration model in Flink. One thing that we had to implement also is a new check for the convergence of the iterative algorithm. Because in bulk synchronous parallelism, you could determine the convergence of your algorithm at the end of the synchronization barrier. Because that's easy. That's where all the intermediate results are aggregated and where you have a single point of checking for the convergence. In still synchronous parallelism, you do not have that single point of checking anymore. And so the condition that we have come up with in order to determine the convergence of the algorithm in this case is that we consider that the algorithm has converged once no more worker can improve on the solution. And that is a check that we do at the side of the parameter server also. So talking about drop-in replacement, that means that in practice, with regards to the API of iterations in Flink, if you want to do iterations with SSP, you would do that the same way that you do with regular iterations. So in order to iterate on your data set using SSP, you just use that command here, specify as usual the maximum number of iterations, if any, and an additional parameter that is the staleness bound of your still synchronous parallelism. So concerning the parameter server, for the needs of our project, we have come up with a quite simple API that consists just of an update call in which you specify the ID of the object, meaning of the model or the parameter you want to share among the workers, along with the clock at which that object is written from the worker point of view, and then the object that you want to store, that is the parameter on that slide here. And the other API is just a get API, a get call, in which you just have to mention the ID of the object you want to retrieve. So concerning the architecture of that parameter server, we have built that on top of a data grid, meaning that the idea is that building that on a data grid, we could directly reuse things such as partition storage, local caching, and data replication among workers for the things that we had to store in the parameter server. So I'm going to talk to you now about a machine learning algorithm that we have implemented using still synchronous parallelism and Flink. And that is the Frank-Wolf algorithm. So the Frank-Wolf algorithm is an optimization algorithm that aims at solving these kinds of problems here. And it's a optimization algorithm in the family of coordinate descent. And in the distributed version that is formalized here, what you want to do is find a linear combination of atoms that will optimize the aforementioned problem. And there's also a constraint over the sparseness of the coefficients also of the solution. But let's focus on the fact that what you need to find is a linear combination of atoms. Atoms can be can be, for example, a family of functions or a set of functions that will your the optimization problem. And so in its distributed version, how does it work? You have your atoms that are vectors organized into columns. So you have a big matrix here with all your atoms. And these atoms are partitioned among the workers. So each worker in the cluster receives a partition of these atoms. So they start with a certain value for alpha. These are the coefficients that you want to find, the coefficients of your for your atoms. These are the things that you want to find. These start with a certain value of alpha. And with that value of alpha, each worker finds the best atoms among the atoms that he has received to solve the optimization problem. So once these atoms are selected locally from the workers, there is a phase where you have a global consensus among all those best atoms. So you are going to find the best among all the best atoms chosen locally from the workers. And from the atoms that are chosen from that global consensus, you recompute a value of alpha based on these atoms and resend them back to the workers. And the iterations go on until convergence. So that's how we would do that in both synchronous parallel. Now, in the star synchronous version, at the beginning, all the workers are going to get the alpha coefficients from the parameter server. There's also a phase where they will locally select the best atoms in their partition of atoms. Then they, without the consensus phase, the workers are going to compute new alpha coefficients from the atoms that they have selected locally. And this they do without synchronizing with the other workers. So there's no global consensus this time. They do that locally on their atoms. Once they have computed the new alpha coefficients based on the atoms they have selected, they update the alpha coefficients that are stored in the parameter server. And then they iterate again if they are within the staleness bounds, obviously. So this was a quite high level view of how the Frank-Wolf algorithm works, of how it is distributed and how it is modeled in using stale synchronous parallelism. If you're interested in the details of, if you're interested in general in this kind of problem, I'll heartily invite you to check out on our publication, the publication that we are going to present next month at the IEEE Big Data in Santa Clara, in which we have the full implementation details, in which we highlight some of the nice properties from the iterate, from the intermediate results in SSP. And in which we also have a theoretical proof of convergence of iterative converging algorithms when on SSP. And so we have applied our distributed Frank-Wolf algorithm on a lesser regression problem using stale synchronous parallelism. We have done that on a cluster of 5 nodes, and the thing is that during the experiment, at each time, we randomly select one node, and during 12 seconds, we launch a process that will put that node under 100% load. So that simulates a case where we have stragglers randomly appearing in the cluster. And this source of straggling is clearly independent from the point of view of the framework. So that's not something that Flink could solve by rescheduling the job from the straggler because of the nature of that straggling. And so these are the results. On the y-axis, we have the convergence of the algorithm, and on the x-axis, we have either the number of iterations or the time spent in the job. So first thing that we might see is that even under SSP, we have convergence. So the algorithm converges well even under SSP, even without a forced synchronization after each iteration. Second thing that we can notice is that under these conditions of straggling and using SSP, you converge in the half of time that you would require when using BSP, that is the blue curve here. And we have also conducted the same experiment without load, and the performance was quite similar from BSP to SSP. Even though in SSP you would have that, you might intuitively think that you have that overhead of contacting the parameter server and having back and forth access to that parameter server. But in practice, we didn't notice any significant difference without load from BSP and SSP. So, as a conclusion, I would say that stragglers are clearly an issue in the context of iterative algorithms, and this is a problem that is aggravated with the size of your cluster. So, the bigger your cluster, the bigger impact you would have in that from these stragglers on your performance. And so, one way of mitigating them is to use stale synchronous parallel iterations. And that's something that you can do now in Flink, because we have 2 pull requests from this research project. The first one covers the stale synchronous parallel iteration control model with the API. And we have another pull request with the parameter server and the implementation of the Frank-Wolf algorithm on the lasso regression problem. So, thank you for your attention. If you have any question concerning SSP or Frank-Wolf under SSP, I'll be glad to answer them.
Thanks for this talk. It was a tough one for me with all the machine learning, but I think very nice. One question on the experiments. So in the BSP version versus the SSP version, I didn't quite get this. Did the BSP version also use a parameter server, or did the BSP version basically have the, let's say, model locally and then like shuffle it between workers, like you can do when you have a strict synchronization barrier?
Okay, so the question is whether the BSP version used the parameter server. It does actually. So yes, it does.
Is there? I mean,
no, sorry. In these curves, the BSP version is indeed a version where it does not use a parameter server, because we indeed have experiments where we use the parameter server but with a staleness bound of 0. And even under this condition, we also have more improvement over the convergence compared to the situation where we are in pure BSP. So yes, this is pure BSP. Sorry for the confusion.
So first of all, I would like to thank you for this contribution. I'm really looking forward to getting this thing merged to Flink. My question is if you are familiar with the project coming out from Carnegie Mellon University, the machine learning framework called PETUM. So in their case, they're using SSP, and the SSPs came out of CMU research. And the second main feature of their framework, apart from the SSP iterations, is the ability to schedule the updates of the parameters, so they are able to, one, schedule updates for parameters more often, let's say for those that have a greater impact on convergence, and secondly, schedule updates for parameters that, or not schedule updates for parameters that have shown to already converged. So using the parameter server abstraction that you're using here with Apache Ignite, do you think that something like that would be possible to implement in Flink also? And how big would the challenge be?
So concerning Pythium, yes, we are aware of that project, and indeed the original proposition of SSP came from the researchers that were working on Pythium. For your question. Is your question? Can we schedule updates and access to the parameter server? Is that the question?
Yeah. Can we affect, let's say, which parameters get updated on the parameter server, choosing, so that we are able to actually update only the parameters that will have a greater impact on the convergence of the model, and not schedule updates for parameters that have already converged according to some metrics?
Okay, we do not do scheduling of access as such, but the thing is that using an architecture based on a data grid, you have things like local. You can force replication of some parameters. So these are things that we can play with. Is that if you have a set of parameters that you know that aren't going to change much, you can force their replication over all the workers. And if other things that we can do also is based on the patterns of access to the parameters. Based on that, we can enforce a particular partitioning policy or replication policy or even local caching policy for these things.
Right. Thank you.
This might be related to the previous question. So how does this relate to delta iterations? So will you still be able to benefit from improvements that you got through delta iterations?
So, sorry, could you repeat the question? Could we benefit?
So how does SSP relate to delta iterations that are in Flink?
To data integration in Flink?
Sorry. To the delta iterations.
To the delta iterations. This has been done on. Yes, obviously. So this concern indeed bulk iterations, and let me think a bit about that. When we started, obviously we kind of consider delta iterations for the implementation of this, and yeah.
In the way we have implemented it, it will not impact it, because in the delta iteration, because the data set is updated on each iteration, it does not change anything on the delta iteration itself, but in the way the iterations are done within each iteration. So we didn't implement it for the delta iteration, but normally it will not change anything.
Is in your experience Ignite or these data grids, are they a good candidate for a parameter server, or how hard would it be to also use it with other kind of systems that would store the parameters?
So the question is what are our conclusions about Ignite, and would we do that again if we had to do a parameter server? So on the paper, Ignite fulfills the job. I mean, all the things like replicated cache, the enforcing of local access within the clients, replication, and the fact that you could specify partitioning policies. All these things fit the bill of what we would expect from a parameter server. But in practice, one of the drawbacks concerns Ignite itself. It wasn't the most easiest piece of software we had to deal with during the project. So I guess the functions from the features of Apache Ignite are good for a parameter server, but Ignite is quite cumbersome to use and to integrate into Flink, for instance.
And thanks for your talk.
Thank you.